Log on, tune in, find out. Another good idea from Cambridge.
Thank you, Mr. Chairman. First of all, I have to repeat some words of Lucia and to thank the organizers for inviting me here. It was somehow first time in my life I could do research for a month, and only research. It's really was a good time here. There are two possibilities, I think, if you want to be successful with numerical scheme. First possibility we were taught now by Ligier: fast, solve everything fast, cheap, good, and you don't know really what you are solving. Yeah. The second possibility, you know which equation you solve, but choose a simple equation. So, and you will also be very successful. And it's exactly what I'm doing. First of all, I have to mention my co-authors. For the first part of the talk, it is Irena Gamba and Wolfgang Wagner. And for the second part, it is Marcia Bisi and Giampiero Spiga from Parma. And altogether, my own experience with granular Boltzmann equation is somehow more or less a combination of very rare events. In the last 3 years, I did something in this, to this subject 3 times. And we published 2 papers, and the third paper is almost finished now here in Cambridge. The equation itself, there's 2 different models we will consider: uniformly heated granular gas and some numerical experiments for this example. The second example is granular gas in a host medium, and again, direct stochastic simulation for these examples, and in the end some references. So the equation is very simple, written here. For uniformly heated inelastic Boltzmann equation, there are 2 main parts: Laplacian in velocity space and inelastic collision operator, written here. I was taught by Alexander Bobolev at the beginning of my considering granular equation: never write the collision operator for granular Boltzmann equation in direct way, because it's very dangerous. Write it always in the weak formulation that is very simple and coincides completely with the classical Boltzmann equation. So I have never written something different than the weak formulation of the collision integral here. Okay, why this equation is interesting for me? To consider full Boltzmann equation, which is spatially inhomogeneous, of course, it is interesting and complicated numerical task, and there's a lot of research in this region, and it is difficult to control the error and to understand all algorithms very clear. It is really difficult because for full Boltzmann equation you have too many discretization parameters. You have the number of particles, you have discretization in x, in t, and so you have at least delta x, delta t, and n. And it is difficult to see something, especially for 2 or 3 dimensional problems. You can see something even for 1 dimensional, it's difficult. And the usual scheme, it is of course separation of physical process. First you produce something like free flow, like in previous talk, and then you do collisions. And for spatially homogeneous Boltzmann equation, for classical, not this inelastic with this Laplacian, there is only 1 parameter for stochastic simulation. This is only n, only the number of particles. There are no delta t. And for this equation, it is possible to introduce delta t. And this, of course, first was done immediately to separate this part, which is more or less diffusion, from this part, it is their collisions. And numerical scheme was introduced delta t. In the first delta t time, there are collisions, and the first time there are kick-ins of particle by this background, which is actually some kind of Brownian motion. And this was the first paper I read concerning with numerical solution of this equation. And this, of course, was immediately clear that something is wrong here, because for spatially homogeneous Boltzmann equation, any kind, it should not be second discretization parameter. It should not be delta t here inside. Yeah. So otherwise you have more errors. And so we decided to see how it is possible to solve this equation without additional discretization and time. So here is a post-collisional velocities written. Here is this E is restitution coefficient. And for our research, we considered this simplified model of collision kernels. Actually, more or less all examples except one, they are for lambda equal to 0, which corresponds to the constant collision kernel, maximum molecules, or hard spheres. For one example, I will show you the results for lambda equal 1/2, something in between. Okay, of course, what we are computing the density, which can be assumed to be equal 1 in this model, exactly the same as for the bulk velocity. You can, if you like, assume it is equal to 0. It is conserved quantity. What is interesting immediately is that the temperature is not conserved quantity for this equation. There is some dissipation of energy due to inelastic collisions, and so, of course, there is some pumping energy in the system from the background Brownian motion. And so, at least for maximum molecules, everything can be computed on the analytical way, and so we have a nice relaxation of the temperature from this initial value, which is defined by initial distribution, to this finite value, which is a combination of this constants in the equation, and alpha is now E, it's a restitution coefficient. Change the notation during the talk, sorry. Here it is still correct, but not here. And it is a nice formula, because if you are interested to check your numerical schemes really up to the end, you have to have something like analytical information about this. And so to have analytical information is everything important, every time important, and for this equation we have even non-trivial relaxation of the temperature and can check this very accurately. Okay, what is the procedure? The general procedure to solve kinetic equations by particle methods is the following. The idea is to approximate this probability density by a family of point measures, so probability measure here is the density by this set of point measures. The velocities are a function of time defined by this system of particles. And we start, of course, with approximation of the initial measure, and then by classical Boltzmann equation, this is some kind of jump process. The process waits for some time without any change, and then suddenly it's changed to the new state after some waiting time. This is microscopic scale. This is not a delta t or something like this. It's much smaller than delta t. And then two particles collide. They change the velocity, and the system is in new state. Again, the state is constant for a while, and then it changes again, and so on. And we count these microscopic time steps until we reach the final time of the simulation. And that's all. What's changed here? In this equation, we cannot simulate on such way. That's clear, because the Brownian motion is continuous process. There are no discrete time steps for jumping, and you have to do something. First, it is continuous, and second, it is unbounded. So it is a problem. And so the idea of these people was, first publications, just to take delta t and to produce 1,000 collisions, 2,000 kicks of background, not collisions, 5,000, and then if the result do not change, we assume that this number of 5,000 kicks is reasonable. And then we go on with this number. Because you cannot do this time counting, because the process is continuous. For discrete process collisions, you can compute this time counter between the collisions. Okay. So, and we discussed this situation, what to do, how to realize this kicking, and the final result was not to kick at all. Yeah. This was because this, of course, numerical scheme with 5,000 kicking for every time step, it's very expensive numerically, yeah, if it is stabilized. And the idea was, why should I know the velocities of the particles between the collisions? I don't need. Only if the collisions will really occur corresponding to the time counter, only what I need to know two velocities. They are velocities of colliding particles. I don't need to know the velocities of n minus 2 other particles. They were continuously changing during this time counter step. And so we kick only these two, where delta t is now microscopic time step. It means once two particles are selected for a collision, I kick them before the collision to get the velocities right, and then I collide them. That's all. The price for this is you have to know at which time your particle was kicked last time. It means in addition to the usual velocities, you need an array of last kicking times for every particle. That's all. And then the difference between last kicking time and this, it is this delta t in this formula. And that's all. No additional discretization parameters, nothing. And of course, to the time steps, really you need actually time steps, not for the process, but just to consider the process, to compute the moments. You compute the moments in some discrete times. At this time, you have to kick all particles to compute the moments, but not to assign the kicked velocities to the particles. So that was the idea. And the result was really fantastic because it was very fast. At the end, very fast algorithm. Actually, no difference to the usual TCMC calculation for the elastic Boltzmann equation. And then for a time counter, you need this Majorand for the kernel of this form. And of course, for all hard-spheres model, usually you can do this with maximal relative velocity. Because the system of particles is always finite, you can find maximal relative velocity of your particle system, something like this. And then you can adapt this value after every collision, after every kicking or whatever. And then you have an algorithm. The price for this upper bound is, of course, you have to introduce fictitious collisions. It means once you have done all work, computed and selected your particles, kicked them, Vi and Vj, it can happen with this probability that you have to reject everything and to start your selection procedure again, not to collide them. It is usual acception rejection procedure, a little bit modified for this situation. Okay. So now I show you the results for this model. We start initially with a pure Maxwellian with a temperature 1 and mean velocity 0, and there are some parameters. So the time relaxation of the temperature is given here, very simple, nice function. You can see this function on the next slide, but first the accuracy. Here's the number n of particles. Here's the maximal error in the computation of the temperature on some time interval for I think 512 points in between. Yeah, maximal error. Here we see the convergence. It means that is this value divided by this value. And we see the factor is close to 4, and the number of particles were increasing by 4. It indicates very clear, known situation that for stochastic simulation of Boltzmann equation, the accuracy in n is 1 over n. It is some constant over n. Yeah. It's clear here. The last column of this table shows the following thing. Due to this kicking, the numerical procedure is not conservative in the mean velocity. It cannot be. Yeah. Of course, the binary collisions are conservative, but the kicking, it is conservative in average if you integrate over the whole space, Laplacian, but of course not for the single kicking. And so we have to control. For this example, the mean bulk velocity was equal to 0. And here's the control of the maximal value on the whole time we have considered. And you see it is also increasing in number of particles. It's stable, nothing happens. It is not 0, of course, but it is small. It fluctuates somehow. Okay. But this is a dangerous value because it's better to have numerical scheme always as conservative as initial equation. but this is not. Here's what I'm showing now. They are confidence bands. This is analytical relaxation of the temperature, and they are confidence bands for 64 particles. And this is your error. Why are always interesting to show such things? Usually the people are saying about Monte Carlo. Monte Carlo is always huge fluctuations, low accuracy, and so on. But in reality, there are two errors in numerical simulation with Monte Carlo. One of the errors is deterministic, due to the finite number of particles, and second one is stochastic, due to the final number of trajectories we have computed. We cannot compute infinite number independent trajectories. I'm always computing something like 2,000 or maybe 1,000 trajectories to get these statistics. And so, the right of these confidence bands show you stochastic error. Yeah? And the deviation of the empirical mean, which is exactly a middle line of this confidence bands, to the analytical solution, it is a deterministic error. And you have to realize as many repetitions in your numerical simulation in such a way that the confidence bands are exactly and probably as well as possible separated from the analytical solution. Otherwise, you have no information about the deterministic error. Confidence band should be separated from what you know, then you can measure the deterministic error. And here for 1024 particles, you can see again that, of course, the confidence bands are smaller and the deviation from the analytical solution is smaller, and so it is corresponding to this table. You can see really the error here.
How you can find this confidence boundaries?
This is normal statistical method. I realized 1,000, for example, 1,000 independent runs of my code. I compute the empirical mean. It's just a sum of all to every time point, sum of all temperatures over 1,000. That is the middle line, what is not plotted. And at the same time, I always compute the squares of all values. And then I compute dispersion actually, statistically, multiply this by 3.2 to get confidence bands up to accuracy 10 to power minus 3 and plot them, that's all. That's really statistically computed values. That they are, of course, not completely exact because I don't know that is a deviation from empirical mean in both directions. Yeah? Okay, but still you have to do this. Otherwise, to show some fluctuating curve from one trajectory, it is not fair to the Monte Carlo method. You will never get information from one trajectory. You need at least, I would say, at least 100 trajectories. And then you can say, are there big fluctuations, are there small fluctuations necessary to reduce variance or not, what is enough, and so on. Without this independent, it is a little bit different strategy for steady state problems. You can do averaging after reaching steady state, but it is strongly a transient problem. I'm not interested to compute this temperature here. I am interested to compute the profile of the temperature and the whole relaxation, time dependent. Okay, one of the questions at this time, it was about maybe 8 years ago, it was a discussion what happens with the steady state solution of this equation. It was clear from the physical literature that there are so-called overpopulated tails. And also in our community, this was studied. I think one of the complete results is in paper by Bobolev, Gamba, and Panfirov, where for this model, this kind of asymptotic behavior is shown. In difference to classical Boltzmann equation, where the steady state is independent of collision kernel, here it depends. And so you have for Maxwell molecules very overpopulated tails, and for lambda equal 1 for hard spheres, you have still here 3 over 2, or not 2. Yeah? And that was, of course, a challenge for every numerical scheme to compute the tails. It is what's really interesting. Temperature computation is trivial. Everybody can compute the temperature, but to compute the tails and to compute the asymptotic of the tails, that is more tricky. And to show the accuracy again of this scheme, we perform the computation for lambda equals 0, 1 over 2, which is exactly the example with a lambda in between, and 1. And this 3 straight line shows the slope 1, 5 over 4, and 3 over 2. And this is the first computation of the tail. This line, it is a really computed tail, because everything is double logarithmic here to see the slope. And you see at the end it becomes more and more parallel to this line, which corresponds also to lambda equal to 0. In the second plot, we see lambda equal 1/2. It is parallel to the middle line. Small oscillation here already, because this tail is already more complicated to compute. It is less overpopulated. And this one corresponds to the hard spheres. And to tell you the truth, I cut it, highly oscillated last part of this plot, not to show this. Here was a little bit oscillations already. But still you can see that it's not parallel to this line, it's parallel to this line. So it has changed. As it was possible perfectly numerically to get an agreement with the theory obtained with physical arguments, with mathematical arguments, all possible. So it was a first thing. What is interesting here? Interesting in such equations where you have two objects, they're simple, they're spatially homogeneous. But because there are two objects, you can study many other things. And for this equation, it is now elastic collision with the background, written here again in the weak form. Here it's of course not necessary. Here we have some background Maxwellian, and this is a linear collision operator here. And here is again inelastic nonlinear collision, a binary collision operator. I don't write this, it is exactly the same as in the previous part. But now the additional energy is coming in the system through the collision with the background, which will not change and not recognize somehow that there are collisions with something happen. It is strong enough. Okay. Again, now we have some post-collisional velocities for the first part, for this linear collision operator, where alpha is now computed with this value. This is a mass of particles in background, and this mass is of particles of our gas. So this alpha collision is elastic, but the masses of particles are different, so the collision transformation is more complicated, but still trivial. Again, we consider these collision kernels. And for this problem, what is interesting, even the bulk velocity is not conserved quantity. Only the density is conserved. And so we have even more analytical information to see what happens with the system. Here, for example, for Maxwell molecules, if you choose lambda equal to 0, relaxation of the bulk velocity is given here. For t equals 0, we start with v0, which is initially given from initial distribution. For t, if t goes to infinity, more and more we will get the bulk velocity of the background Maxwell. And the same is true for the temperature. We start with the temperature T0, and we end up with some temperature d over c. We skip now here all notations for this 5 constant a, b, c, d. There's just boring combination of pi and c0 and restitution coefficient or whatever. Only what is interesting in this final d over c temperature, of course, in any case, you can see that it is less than the background temperature. It means this inelastic collision takes some energy away. And of course, it is a possibility to try to construct the following thing. If inelastic collision are somehow weak, it means the constant in front of this is small, and we start with initial temperature which is equal to background temperature. It should be some non-trivial curve at the end for the temperature. And initial bulk velocity should differ significantly from background velocity. In this case, I assume I will get not such a simple relaxation like in previous case, but more non-monotonic curves for the temperature. And this is exactly the case what we can see in examples later. But okay, let's again continue with stochastic simulation. What to do? The same approximation of initial measure by a system of particles. Now we have this process, both are jump processes, collisions, and then but there are two, and so the time counter parameter is now a sum of two time counters. This is for linear equation, this is for non-linear equation, and pi hat is the sum of the both, which means the jumps times they are exponentially distributed with this parameter. And to compute these parameters, you need to sum up. First, you have to integrate collision kernels with background Maxwellian in the first case for any particle. And for second, you have to integrate your kernel over the unit sphere only for both particles chosen for the collision. And then you have to sum up over all particles, or here and here. And so you will get P2, P1 and P2. This P1 is a mistake, sorry for this. It is a P2. And of course, again, for this, we will use some Majorans, the same as the previous maximal relative velocity. But what to do with this? Here is no possibility to choose maximal relative velocity because it is unbounded value. And so in some, as I realized this, it was clear that practical realization of this numerical scheme is a little bit more complicated than I have thought in advance, because due to linear collisions, not because of inelastic nonlinear collisions. The second difficulty is the following. Once, of course, these parameters are computed, we choose elastic collision with this and inelastic collision with this probability. And for elastic collision, you cannot choose the particles uniformly. You have to choose the particles corresponding to these discrete velocities, where this exactly this function is given here. And once you have produced this index I, you have to generate a velocity from background not corresponding to the Maxwellian, but corresponding to this non-isotrope density. If here is bulk velocity differs from this Vi, then this density is non-isotrope, it's really three-dimensional. It is possible, but it is a complicated numerical task for every collision. And what to do? And the result was that the following. It is, of course, easy to generate this and then to perform the collision transformation. For maximal molecules, there are no problems, actually, because everything is constant, and you can compute P1 and P2. And as usual, if it is everything here equal to 1, then the time steps for linear collisions is 1 over n. 1 over, and for nonlinear collisions is 2 over n minus 1. It's very simple, and also very simple to get a collision partner from background. You have to generate this velocity according to this density. This is normalized background Maxwellian. There's no problem. On this parameter, collision parameter omega, is uniform. Okay, let's consider again the same example. We start with this Maxwellian with a bulk velocity 0 and temperature 1. By background, we choose different bulk velocity, not 0. So strong difference here, but the same temperature 1. And so we can see this relaxation of the bulk velocity and this relaxation of the temperature due to these previous numbers A, B, C, D. And there's again table of accuracy. Here we start even for particle number 4. For this model, reasonable results can be obtained. Yeah, and you see the accuracy by 1,000 particles is already 10 to the power minus 3. It means if you try to plot these curves, you will not see any difference optically, even for 1,000 particles. And that is to discussion how many particles you need to solve the Boltzmann equation in an accurate way. Yeah. Here's convergence factor again. I increase by 4. I see 4 here. And this is a confidence bands. Confidence bands. And again, I increase the number of particles by 4 and number of independent trajectories at the same time by 4. So I have to see the convergence of the thickness of confidence bands by 4 again. It is perfectly given here numerically. Huh? Cannot be better. Okay, there's the curve. Look at this. This is a relaxation of second component of the bulk velocity from initial 0 to 1 at the end by 4 particles. Now I don't plot this confidence bands, but only this empirical mean. Yeah? And even by 4 particles, this is of course very low moment, first moment. Yeah? It is perfect. On the second plot for 16 particles, see here and there you see a little bit differences. There are 16 particles and 256 independent trajectories. For this moment, it is already perfect. Again, relaxation of the temperature. The analytical curve is given here. As I promised you before, it is no less trivial because we start at 1 and we finish somehow a little bit less than 1 because there are still inelastic collisions. But because of the strong difference of at the beginning at least, of the bulk velocities of the both media, we see this increase of the temperature and then decrease. And this is computation for 64 particles. And here you see the confidence bands. And here I have plotted empirical mean too. This curve and this curve coincide, it's the same. Okay, that's good, but you see the error. But for next step, by increasing by 4, you see already more or less perfect agreement between analytical and numerical solution. And for 1000, you cannot see the difference. The line coincides simply. So next, hard spheres. What to do here? We have this kernel, and the obvious idea is to find a majorant for this kernel on this form first. To introduce this background velocity here, background velocity, and declare this as a upper bound for our kernel. Of course, it is still non-trivial because now we have to compute this value. These integrals can be computed analytically. This is now very simple because now the UB and UB in background Maxwellian is the same. And here it is a constant leading to this density only by integration. And of course, we have to change as a time counter. It will be bigger. It means if time counter parameter is bigger, the time steps are smaller. But some of the collisions will be rejected because they are fictitious. This is the idea. And then we have these probabilities for every particle. They are still unequal. And so you have for every collision realize an index from a set of unequal probabilities. If you do this on the classical way, you will need something of n operations for every collision because you have to sum up. In the average, you will fit somewhere in the middle. Yeah. And so I realized for this so-called Euler's algorithm from the literature, which is actually proved to be capital order of 1 operations for every realization, not capital order of n. It is again some acceptance rejection procedure here. It is more non-trivial than the previous realization. But drastical simplification is here. Now we don't need to sample from the complicated non-isotropic density function, but because here we see that is the sum of the both multiplied by Maxwellian. This is trivial, sample from Maxwellian with some probability, with additional probability, sample from some distribution which is less trivial than Maxwellian, but in any case it is isotrope. It means you have to choose a vector uniformly distributed on the unit sphere in 2 dimensions in spherical coordinates, and we have to sample only a single value for the radius, 1-dimensional distribution. And that is easy in any case. So it can be realized efficiently. Together with this alias algorithm, everything is fine. And again, the same results. We choose a parameter in front, multiplier in front of the inelastic collisions much smaller than pielastic collisions. And in this case, I have no, of course, for hard spheres, I have no analytical information. It's not available. But what is available is a series of hydrodynamics models. And one of these equations was derived by Biese and Spiegel some years ago. I think it's published in 2007, something like this. And this is this. This is quite complicated. Of course, we see that the bulk velocity relaxation to background velocity is given. Here, this equation is more complicated. Maybe it is possible to solve in an analytical way. I didn't try. I solved just this system of equations by Runge-Kutta method of the second order, to get the curves for investigation of the accuracy. And that is some plots for this. Again, I take n equal to, it's clear that the curve is very similar to the analytical solution for Maxwell molecule. It's a little bit stretched, a little bit different values at the end and here in the maximum, but very, very similar. And again, I see a perfect agreement. Now this dashed line indicates the solution of the previous system of ODEs obtained by Runge-Kutta second order. Yeah? And this stochastic line corresponds to the numerical solution of the Boltzmann equation, what I assume to be the true now. Now it's opposite. Now the numerical solution is the true, because previous one was hydrodynamic model. And you see, as I first saw this curve, I said, oh, God, this is exactly the same. There's no difference. But actually it is a difference. There are still, for 64, you have still some stochastic fluctuations here. If you remove them, you see that you have a difference here and then the final temperature. This is a disagreement between hydrodynamic model from the Boltzmann equation. Now I would say this thin line is the correct one. And this is the model. And this one is the model, hydrodynamic model, solved by Runge-Kutta. Okay, now we can think this small difference is because the deviation of initial Maxwellian is rather small due to the inelastic collisions are very weak, this factor. Okay? Then this, we take this constant equal to 1, and then there's no overshoot of the temperature. Now it is this loss of energy is strong enough at the beginning. The temperature is now monotone function in time. That is a solution of the Boltzmann equation, more or less without any fluctuation. Also qualitatively good solution. It takes about maybe 1 hour on a computer to get this. All previous computational time is seconds. You can forget this. I don't speak about flops here. This one with 1,000 particles and 15,000 independent trajectories, says confidence bands are 10 to the power minus 3. You cannot see them. And so we have here, I would say, now big deviation, visible deviation from both solutions. I think this is a solution of Boltzmann, and this is a curve of hydrodynamic model. Yeah. Okay. First, I thought to give some overview over the literature to granular Boltzmann equation, but then I realized that except of Aoki with A as his name at the beginning, it is almost impossible because I have to start with Biese, Bobolev, Carrillo, Cerciniani, Gamba, Ilna at the beginning, and I have to finish somehow with Spiegel, Toscani, Villani, and Wagner. Okay, so I skip this and give only 2 papers where I am involved. First is this with uniformly heated granular Boltzmann equation 2005, and the second with Wolfgang Wagner. Exactly here discussed this problem of this splitting, yeah, with strong splitting, trivial splitting, and so on. It is very difficult to study for full Boltzmann equation, especially inhomogeneous. It's very easy to study this for this equation. And we have only two parameters then. We can introduce delta t and to split kicking from collisions. And then you have additional error. And you have to you can study this error by trivial splitting, by strong splitting, or by our scheme without splitting. And so you can see that the direct DCMC is much more accurate. Trivial splitting is delta t scheme, and strong splitting delta t square splitting. It is these results are given in this paper. And this paper is of course now in progress. It's almost finished because the results are the theory. We have to polish this and to submit. And so I have to thank Newton Institute and organize again for this opportunity to finish this paper here. Thank you.
Okay, any questions? Yes, I was maybe I missed a point. What is the rate of of cooling you have in the hard spheres case?
The constant was 1. Constant in previous example was, of course, one of the both constant on fronts of both collision operators you can always choose to equal to 1. And so we did this for linear collisions. On what is on front of the second one, it is somehow a ratio of both number densities, and it is your freedom to choose some additional parameter here. And so for this overshoot of the temperature, it was parameter 1/8, and for this monotonic decrease of the temperature, it was parameter equal to 1. So the collision kernel was exactly modulus V minus W.
Okay. Okay, so you take, you have your bilinear collision in elastic plus a bath. My question is, what is the rate of the convergence to the equilibrium temperature?
That's a rate of convergence to equilibrium that I didn't study. I don't know.
From the scheme, you
I can see, of course. I know that for this setting of parameters, it is, of course, given if you increase all parameters, relaxation in collision kernel is by factor 2, then you will get a relaxation 2 times faster. That's clear, yeah? Because you just double the number of. But if you keep something constant and change another parameter, you can see something. For example, Maxwell molecules, 1,1 in front of the boss with Maxwell molecules relax for this example in the time which is 1.5. Okay? But if you choose the same parameters on front but hard spheres, the corresponding relaxation time is 0.5. It's about 3 times faster.
Okay, my question was to see if by your method you can see the half flow that you have for hard spheres.
Here you see, for example, this hard spheres example, and here you have for a long time already everything constant.
Yeah, because there is a difference between inelastic Maxwell and hard spheres.
Yeah, by factor 3.
Well, I'm not sure I understand what you say about constant and factors, but you have exponential convergence for a Maxwell inelastic of the temperature, and you have polynomial convergence the inelastic hard spheres case.
No, for at least for the temperature analytical results, even for this, you can directly show that it's exponential.
Yeah, but what does this model come from? There is no rigorous derivation of hydrodynamics at now.
It is. I choose this from the paper of Pisi and Spiegel. It is derivation assuming, for this example, I think just assuming that distribution function is just Maxwellian. Then you can derive this. Of course, it is wrong, but you see how wrong is it? It's a little bit wrong only.
No, but it is not Maxwellian.
No, of course.
In the long time, you pay. This is an error which you pay. Because we made some proof with Stefan Michler of the half flow.
I know that some.
You can see numerically.
Yeah, maybe, but I didn't try to see really from the numerical point of view at which time I achieve real equilibrium. For this set of all parameters, I just try. First, to take time equal to 5 and to see If the curve something like this, then I cut this, and 1.5 was perfect for curves, actually, not more.